choosing 4 designs that would go through something called the generic design assessment. So when we built Sizewell B, we got ourselves tied up in knots in terms of how to go back to what is a neutron. Essentially, I'm being slightly facetious here, in terms of assessing the safety of Sizewell B. And Sizewell B took an inordinately long time to get through the initial safety processes. And then when it was going to go to the next place that reactor was going to be built, they wanted to start all over again, right back at what is a neutron. And of course, it's an extraordinarily inefficient way to behave. So we've engaged in something called the generic design assessment. And the best analogy is that imagine you build a new airport. You don't go back to deciding how a Bernoulli's principle works for wing designs as to whether or not your aircrafts are safe. You accept that the 747 or the A380 or whatever it is commensurate with the design of your airport. But you don't ask whether or not the A380 is safe. There is a design assessment on the A380 already which says that it is safe. And the idea was to go to do the same with these 4 designs, is to have a generic design assessment capability. And then you just look at specific local issues associated with things like the amount of coolant water and the type of coolant water provision that you would have, and was it commensurate with these sorts of reactors. Anyway, very quickly, actually 2 of those designs dropped out. The Canadian CANDU reactor and the ABWR both dropped out, and the EPR, AREVA, and the Westinghouse AP1000 designs went forward. And these are all going through in a market-driven process. It's the first time really that market processes have defined these. And what happened is, quite quickly, there was a bit of a switch, and the ABWR Hitachi, because of the buying of certain areas and the buying of companies from the UK, came back online, and the AP1000, which the Westinghouse lost out to a certain number of bids, and they put that back on the back burner. And then NewGen came in, collaborating with Iberdrola and GDF Suez, and then Toshiba bought out Iberdrola, interested in this, and so you can see it got complicated. And where we're at the moment is that we're back to having these 3 reactors going through the generic design assessment process, and the EPR has gone through. And the ABWR, so this will be the first time boiling water reactor for generating electricity, would have been built in the UK, and the AP1000 is now continuing back along the pathway. Our regulator doesn't have the capacity at the current time to look at any other designs. So the reason no other designs primarily are going to be looked at in the short term, including the Russian design, is frankly because we just don't have the capacity to do the GDA. I know the Korean reactor designers as well would be keen to get an assessment, but we just can't do that. So in terms of the EPR, it has the kind of features that you would expect, and again these are all sort of figures that you can get from AREVA. Double wall containment. It has this core catcher, so in case the core actually was to melt, then it would be completely contained within the reactor. It has 4 train redundancies. In other words, it has 4, 1, 2, 3, 4 heat exchangers, which gives you again additional redundancy. But it's a fairly straightforward, if rather complicated, design. The Advanced Boiling Water Reactor, this is Hitachi's design. There it is, just there. And it has the sort of features you'd expect from a boiling water design, including, interestingly, the control rods move from the bottom up in a boiling water reactor, because here's the core, you boil the water, and the steam goes up, water droplets are separated out so that you get dry steam. I'm sure that everybody knows that when you look at your kettle boiling in the morning before you make your cup of tea, this white stuff you'll see coming out the spout is not steam. You call it steam, but it is not steam. It is water droplets entrained in steam. Steam is a colourless gas. And if you don't separate out the water droplets here, when that hits the turbines, it will ruin the turbines in a matter of certainly a few minutes, because of the velocity and of the water particles. So all of this, that's the core. All of this stuff up here is trying to dry the steam. I always think that's interesting. People who don't know much about steam. But the issue that the regulators in the UK will have to get to grips with is the idea that the control rods are forced up from the bottom against gravity, whereas in a PWR they fall down from the top with gravity. Because in a PWR you don't produce steam, you have a secondary, you have a heat exchanging process. And then finally there is the AP1000, and the AP1000 incorporates, the AP1000 incorporates so-called passive features, which are arguably generation 3 plus types or features, but people get very upset and think, is it 3, is it 3 plus, is it? And, but anyway, the point here is that two things. You have a water tank here, there's the reactor core, and so the water is fed down under gravity if there was some form or reason for there being a breach or an interruption in the cooling system into the core of the reactor. That water then internally circulates, and then there's a water tank on the top of the reactor, although that's going to be a concern for our regulator, because the idea that seismically that you have a structure like that with the most of the weight on the top of it, you can see that is a challenge to convince the regulator, but nevertheless, the water tanks on the top, those cool the outside of the reactor here. So the idea is that the decay heat, which is what caused all the problems in Fukushima, would not be an issue for this design. However, as I've pointed out in a couple of publications, not necessarily to everybody's happiness, is that water tanks you've got to be able to refeed water into the water tanks. So it's not truly passive, it's transiently passive. The use of the word transient is my word. It isn't necessarily other people's word. That may be very unpopular for a little while. That's okay. I mean, there's all sorts of, I have to say, from a personal and research point of view, I do think the APWR is very interesting, and in fact there are other designs which take advantage of it. But in the core here, because you get nuclear boiling, so the water comes up onto the fuel pins, and it boils onto the fuel pins and produces this wet steam that then goes up and gets separated off. But as you move up the fuel elements, then because you've got less water, then the neutrons, moderation, so the energy of the neutrons goes up. So that actually the spectrum of the neutrons at the top of the core is different than the spectrum of the neutrons on the bottom of the core. That's quite interesting to somebody like me who's interested in nuclear fuel, because it means that the type of actinides, the isotopes that you get at the top and the bottom are going to be a bit different. And actually there isn't a tremendous amount of research that's being done for high burn-up fuels, or fuels that have been in the reactor for a long time, looking at the effect of those different neutron populations. And that's something that I'm quite interested in, because theoretically you could burn up some of the long-lived actinides in those sorts of designs. So that's quite interesting.